Every Arduino sketch starts the same way. You want something to happen once a second, so you reach for delay. It works, right up until you need a second thing to happen at the same time. The trouble is that delay does not wait. It burns. The processor sits in a counting loop, unable to read a sensor or answer a button. There is hardware on this chip that counts for you, and it never asks the processor for permission. Let us look at what that hardware actually is. Strip away the words, and a timer is one thing. A register that counts. The 16 MHz crystal on the board produces a steady stream of pulses, and each pulse adds 1 to that register. Nothing in your program drives it. The counting happens in silicon beside the processor, not inside it. That register has a width, and the width is the whole story. 8 bits hold values from 0 up to 255. The next pulse has nowhere to go, so the count rolls back to 0, and the chip raises a flag to record that it happened. That flag is the timer telling you something occurred while you were busy elsewhere. You can read it later, or you can ask to be interrupted the moment it is set. Now compare that with delay. Delay produces the same weight by spending every processor cycle on nothing at all. The timer produces it by spending none. One costs you the whole machine, the other costs you nothing. 3 of these counters live on the UNO, and they are not identical. The chip gives you 3, and they are already employed. Timer 0 is 8 bits wide, and the Arduino core has claimed it. Millis, micros, and delay all keep their time from it, so reconfiguring timer 0 quietly breaks every one of them. Treat it as spoken for. Timer 1 is the interesting one. 16 bits wide, which means it counts to 65,535 instead of 255. That extra width is not a small upgrade. It decides how long an interval you can measure before you are forced to slow the clock down. The servo library uses it. Timer 2 is 8 bits again, and it drives tone. It also offers 2 prescaler settings the other 2 lack: divide by 32 and divide by 128, which sometimes makes it the only one that lands exactly on the frequency you want. 6 pins on this board can produce pulse width modulation. That is where the compare hardware earns its name. A digital output pin has 2 states, on or off. There is no setting for half. And yet you can dim an LED smoothly because your eye and most physical loads respond to the average, not to the instant. So the chip switches fast and controls the ratio. That is all pulse width modulation is. The counter climbs, and beside it sits a second register holding a number you choose. Dedicated hardware compares the two on every single tick. While the count is below your number, the pin is high. Once it passes, the pin goes low. The comparison itself is the output. Move that number, and you move the crossing point. A quarter of the way up, and the pin is high a quarter of the time, so the average sits near 1¼ volts. 3/4 of the way, and the average follows it. You are not generating a voltage. You are generating a ratio, and the load does the averaging for you. The processor writes that number once and walks away. Everything you see after that is produced by hardware. But there is more than one way to climb the ramp. The counter does not have to count in one direction only. How it climbs changes the waveform you get, and every mode trades something away. Fast pulse width modulation is the simple one. The count ramps from bottom to top, resets, and starts again. One slope per period, which gives you the highest frequency the timer can produce and the full resolution of the register. The cost is that the pulse edge moves as you change the duty cycle, because only one end of the pulse is anchored. Phase correct counts up, then counts back down, Every period is now 2 slopes instead of 1, so the frequency drops to roughly half. What you buy is symmetry. The pulse stays centered on the same point in time no matter how wide it gets, which matters when you are driving a motor bridge and both halves have to stay balanced. Phase and frequency correct looks almost identical, and the difference is one detail of timing. It updates the compare register at the bottom of the count rather than at the top. If your top value never changes, you will not notice. If you are changing the period while it runs, that detail is the difference between a clean sweep and a glitched cycle. Choosing a mode means writing particular bits into particular registers.
Everything a timer does is decided by 3 registers, and the first thing to understand is that you never think about them as bytes. You think about them as groups of bits, and each group answers exactly one question. TCCR1A and TCCR1B are the control registers. Between them, they hold the waveform generation bits, which choose how the counter counts, and the clock select bits, which choose how fast. TIMSK1 is the interrupt mask. Setting a bit there is how you ask the chip to interrupt you instead of making you check. Now watch the setup. Clear both control registers first. The Arduino core may have configured this timer before your code ever ran, and one leftover bit will produce behavior you cannot explain. Zero the count so you start from a known state. Load 15,624 into the output compare register. That is the top value, and where it comes from is the next scene. Set the waveform bit that selects clear timer on compare match. Set the 2 clock select bits that together mean divide by 1024. Set the interrupt enable, then call the global enable last of all, so the timer is fully configured before it is ever allowed to interrupt you. 8 lines, and after that, the hardware runs alone. Your loop never touches it again. But the number 15,624 was not a guess, and it is worth seeing where it comes from.
16 million ticks a second is a great deal of resolution and very little reach. At full speed, each tick lasts 62.5 nanoseconds, and a 16-bit counter fills up in about 4 milliseconds. If you want to count a whole second, you have to slow the clock down before it ever reaches the counter. That is the prescaler, a divider sitting between the crystal and the counter, offering divide by 8, 64, 256, or 1024. Timer 2 adds 32 and 125. Each step makes every tick longer, and every reachable interval longer with it. So sizing a timer comes down to one question. What is the smallest divider that still lets my target fit inside the counter? Take 1 Hertz on timer 1. 16 million divided by 65,536 gives 244.14. Round up, and anything from 256 upward will work. Pick 1024. 16 million divided by 1024 is 15,625 ticks per second, minus 1 because the count starts at 0. 15,624. It fits comfortably inside 16 bits, and it would never fit inside 8. Now the timer knows when. It still has to tell you.
Polling a flag means asking. Your code has to come back and check, and if it is busy elsewhere, the answer arrives late. Interrupts remove the asking entirely. Set the enable bit for the compare match, call the global enable, and from that moment, the hardware watches on your behalf. The instant the flag is raised, the processor stops what it is doing, jumps to your handler, runs it, and returns to exactly where it left off. Timer 1 offers 2 of these, one for the compare match and one for the overflow. The handler comes with rules, and they are not style preferences. Keep it short because the rest of your program is frozen while it runs.
Mark anything shared with the main loop as volatile, or the compiler will optimize away reads it believes are pointless. Never print or delay inside it, because both depend on interrupts that are currently switched off. Set a flag, increment a counter, toggle a pin. Do the real work outside. Now put all of it on one board.
Here is everything together, and it is 10 lines of setup. Timer 1 is configured exactly as before. Clear on compare match, divide by 1024, compare value 15,624, interrupt enabled. That gives a 1 Hz heartbeat driven entirely by hardware, toggling a pin from inside the handler. Timer 2 is set to fast pulse width modulation, with no prescaler at all. 16 million divided by 256 is 62.5 kHz, far above anything your eye or a motor will ever notice. A compare value of 63 means the pin is high for 64 ticks out of 256, which is 25% duty. 1 slow square wave and 1 fast carrier, running at the same time on the same chip at frequencies 4 orders of magnitude apart. And timer 0 was never touched, so millis and delay still work normally. Now look at what the loop is doing. Nothing. Both waveforms continue whether your code is idle, reading a sensor, or driving a display. That is the whole difference. Counters run in hardware. Compare units shape the output. Prescalers set the reach. Interrupts hand control back to you exactly when it matters, and not one cycle before.